Thank you. It's lovely to be back. I did my PhD here at the IOA, so it's really beautiful to be back. Thank you for sharing this space with me. So I'm going to tell you a little bit about, the genealogy tree, not of every single atom in your body, but some primary atoms in your body. So we are incredibly numerous in terms of our atomic nature. So we have 10 to the 28 atoms in our body. That's in non-scientific notation, a 1 followed by 28 zeros. So we have more atoms in our body than stars in the universe. The grains of sand, in the entire surface of the Earth. And those atoms are so incredibly durable that, if your hydrogen atoms would whisper to you, they will tell you about the beginning of the universe and the Big Bang. So ultimately, what I'm going to try to convince you is that all of that cosmic history is indeed in your bodies. No? Exactly, sound effect. Now, I decided to start because, we as humans are relatively self-centered. The vast majority of our mass is made of oxygen. So oxygen is 65% of our mass. Carbon is about 18%. Hydrogen and nitrogen. So those are sort of our primary components. So I'm going to tell you the story about oxygen, which should be the most important atom in the universe, given that you're primarily made of it. And if you think about H2O, water, oxygen carries the vast majority of the mass. So there it is. So the story of oxygen is intimately linked to story of a very massive star. So in astronomy, we call massive stars anything that it's about 10 times the mass of the sun. That has 10 to the 58 atoms. And these stars basically go through an very, very short lifetime. They're incredibly luminous, but have very short lifetimes. They're sort of the Elvis Presley of stars. They're incredibly luminous, but they live for short periods of time. And what they do is they fight gravity by fusing elements in the core. Yeah? And these massive stars are able to get all the way to iron until they get their fusion all the way to iron. And as you know, or you may not know, iron is the most stable nuclei in the universe. So once you arrive to iron, there's no more reactions that are viable, and gravity has won the battle. Yeah? And that massive star, especially its core, will collapse. And that collapse will be halted once the densities get incredibly, incredibly high to nuclear densities. And what you're going to see here is a visualization of a realization supercomputer simulation of the formation of a neutron star, which is the object that ultimately halts the collapse, that accompanies these supernova explosions. And these supernova explosions are the ones that are basically synthesizing and sharing the atoms of oxygen in our own Milky Way. So this is a really beautiful visualization that we made in the California Academy of Science. Carl Thiel's my colleague. And what you see is a star that it's about to lose its battle against gravity. It's a red giant, so it's incredibly, actually we'll do this. And we're going to zoom about 6 orders of magnitude into the interior of the object where we actually see the iron core. Now, the things that you should see is that, stars are very dynamical. Burning produces a lot of heat, so there's a lot of convection and turbulence inside. And we are slowly going to go inwards where basically the iron core realizes that can no longer sustain its battle against gravity, and gravity basically starts collapsing its core. Now, in those collapses, we attain temperatures that are billions of degrees Kelvin, and we get densities that are close to nuclear densities. No? So these are sort of the largest temperatures and densities that we can attain in the universe after the Big Bang. So there you go. What it's kind of highlighted there is the size of this protoneutron star. And what you see here, as material falls back, you see the pressure slowly increasing. You can think about a pressure cooker. As heat continues to increase, the pressure starts to increase until this is actually able to halt the collapse. And something that it's amazing is that the particles that are mediating the energy and momentum transfer in this interior are neutrinos. So neutrinos are produced copiously in this interaction. Even though we think of neutrinos as not being very interactive, they're essential for us to produce oxygen. And all of what you see here will be sort of the oxygen layers in the interior of the star, which are actually going to be exploded. Yeah. Now, all of this simulation in human time lasted about 0.1 seconds. So in a fraction of a second, the iron core collapses and the supernova explosion actually takes place. I think there's a flash. No, there's no flash. No flash warning. And then the external layers of the star are basically thrown into space. So something that it's amazing about the supernovae explosions is that they're so incredibly bright that we can see them from very, very far away. So this is an example of a core collapse supernova, the collapse of a massive star, which we see it in an external galaxy. And the supernova together is as bright as all the stars of that galaxy put together. So as a result, we can see these oxygen production machines, very, very far away in the universe. So this is a visualization of a local, this is of course a drawing, a cartoon picture of a red giant collapsing, that it's ultimately going to form the Crab Nebulae, which is one of our closest neutron stars. And ultimately what it's left behind, all of what you see here, the vast majority of those filaments are oxygen. Yeah? So the oxygen in your bodies once resided in this beautiful filamentary structure, and in the interior, what you find in most supernovae is a neutron star. And in some cases, the neutron star can be a pulsar, and that's how we see. So this is particularly in the Crab Nebulae. We see the pulsar, and we see basically the remnant of that explosion. So the way that I want you to think about this is about the recycling of these metals in the universe. You have these supernova explosions. They throw this oxygen that is freshly synthesized, and it gets mixed with other oxygen from other supernovae and so forth, and then mixes, creates new clouds, new stars come to light, and the recycling continues. Yeah? And this is going to be a central theme for a talk to try to think about, well, how many generations of supernova we have in our bodies. No? Now, supernova are not only amazing in terms of their production of heavy elements, but they also provide the vast majority of energy deposition in galaxies. So what you see here is a hydrodynamical simulation of a Milky Way-like galaxy, and you see these outflows that are basically emanating from the galaxy. All of that is driven by supernova explosions. So the way that I want you to think about this is that supernovas are happening all over the Milky Way. They're producing so much energy, they're producing turbulence, and they're basically getting constantly mixed across the Milky Way. So as I will show you, your oxygen atoms have actually crossed the entire Milky Way many, many times. Yeah? When you think about that we haven't left as human or solar system, your oxygen atoms have. And that's going to become a theme of our talk today. Now, the reason why I really love oxygen is not only because the vast majority of our body is made of oxygen, but also because we have this beautiful oxygen atmosphere. Yeah? And what happens? We don't lose a lot of atmospheric oxygen. So that oxygen has been there since the beginning of time. Now, I'm incredibly lucky to be in this room with you all. You more or less breathe about 300 or so liters of oxygen every day. So while I'm sharing this space with you, I'm actually stealing your oxygen atoms. Yeah? So imagine all the history that you have in your bodies, all of these multi-generations of oxygen atoms that have constantly been recycled. So you can think about, okay, how many oxygen atoms do I have of someone in the history of Earth that I really admire? Well, the answer is that you have about 100,000 atoms of oxygen that once belonged to Frida Kahlo. Remember, you have 10 to the 28 atoms, so this is a small fraction. So if you're feeling not very creative, no, you just have to kind of focus on those 10 to the 5 atoms that you have from Frida Kahlo. Now, your body is basically the human history put together, because there's people whose oxygen atoms you don't want to listen to in the history of our world. But in general, you can think that the multi-generations, not only of humans, but of animals, reside in your body. And the thing that is most amazing is that the oxygen atoms that you were born with no longer belong to you. Yeah? So you're constantly recycling. So this idea of constant recycle is something that I want you to kind of grasp when we think about the universe in general. Now, the research that I do is not thinking about how elements that are less heavy than iron form, but heavier than iron. So how elements that are, very, very heavy form. And in particular, there's 3 elements that are going to become incredibly important for our story: uranium, platinum, and gold. Yeah? And I'm going to choose gold as a representative of these really unusual pathways of nucleosynthetic pathways that in fact started by Fred Hoyle and collaborators in Cambridge, thinking about how we make those. And something that I want to emphasize, that platinum and gold are incredibly important for humanity, but in reality, thorium and uranium should be one of the 2 most important elements that you should keep in mind, because the radioactivity is actually keeping the Earth's magnetic field alive. Yeah? So why these elements are essential to life is that if they were not here, we wouldn't actually have a magnetic field, which basically protects us. So habitability is intimately linked to these elements, even though they're a very, very tiny fraction of the total mass of the universe. So how many, we talked about oxygen atoms. How many gold atoms you have in your body? You have about 10 to the 18 gold atoms in your body. If you eat a lot of sushi or large fishes, you probably have a significant enhancement of heavy elements in your body, because they basically store a lot of these heavy elements. That's why sometimes it's dangerous to eat fish, particularly in polluted areas. But you have about 10 to the 18, which that's about a fraction of a gram in your body. But just to give you a feeling, in relative abundance, you have 100 times more gold than the sun or than the universe. So again, if you're not feeling very important, just remember that. So, how do we form these elements that are heavier than iron? And particularly because these charge reactions can no longer give you heat, so you actually have to give energy to the system. And if you want to build a recipe for gold, you need 2 neutron stars, 2 of the densest objects in the universe in pairs. You need them to merge, generate billions of degrees heat, and then the merger of these 2 objects, we believe, ultimately leads to a black hole. So I'm going to guide you through that thinking. But before, I wanted to give you a little bit of a feeling of what a neutron star is. So this is where I'm from, or where I reside. This is Santa Cruz here. And this is Lick Observatory, one of the oldest observatories in the US. And this basically gives you the scale of a neutron star compared to the Monterey Bay. So, a neutron star is the size of a city. It's about 12 kilometers in size. But it has the mass of the sun. Yeah? So it's incredibly dense. is 10 to the 15 times denser than water. So if we were basically standing in the surface of a neutron star, which is not recommended, and I wanted to escape its gravitational pull, I have to actually move at 30% of the speed of light to be able to leave the surface of the neutron star. So they're incredibly dense and incredibly gravitationally powerful objects. Let me give you, I'll turn the lights off. So this is a really beautiful map of the neutron stars that we have discovered to date, and we discover them because they're pulsars. So you can see the flickering, which is being altered just so that the movie looks pretty. Now you can see that as humans, we're incredibly biased towards where we detect pulsars. You can see that we detect them closer to our neighborhood, but we cannot see through the galactic center because it's incredibly, a lot of the radio emission basically gets absorbed and dispersed. We expect in our own Milky Way to have of the order of about tens of millions of these neutron stars. And we have discovered tens of thousands of them. So there's a huge, vast parameter space of discovery. Now, of those 1,000 neutron stars that you see there, I want you to point to me 10 of those have another neutron star as a companion. Of course, I don't even know where they are, but that just gives you a feeling that these objects, these two neutron stars, are incredibly rare phenomena. However, we owe the vast majority of the synthesis of heavy elements through these collisions of neutron stars. Yeah? And currently, we have discovered 12 neutron stars that have another neutron star as a companion. Yeah? So what happens to the system? So these systems are incredibly compact, and because of that, the distortions of space and time that they have really large amplitudes. And those amplitudes can carry both energy and angular momentum away from the system. And what happens is that these neutron stars spend hundreds of millions of years dancing together until finally they're able to kiss. And it's in that ultimate coming together that we feel that the conditions of the right temperatures and densities are basically achieved to produce these very heavy elements. This is actually a simulation that I actually ran in Leicester during my PhD of two neutron stars basically coming together. And what you see here is entropy. So you're seeing when these two objects touch, they create a huge amount of heat. And we believe that if you look at the tidal tails, these two tidal tails, about a fraction of a solar mass is able to escape above the escape velocity of the system with the right conditions to actually produce the vast majority of heavy elements in the universe. And again, a neutron star is formed in a fraction of a second, and gold is basically produced in tens of milliseconds. Yeah? So these processes are really, really prompt and require incredibly high densities. Particular neutrons, you need a huge number of flux of neutrons. So this is where we were theoretically. We said, well, as these two objects merge, this material that is ejected is radioactive, is constantly decaying, that heats up the material, and at some point it's going to become transparent and we're going to see photons. And the prediction is that we expected an optical transient that would last about 1 week. So it would appear and then disappear. Yeah? So we had made all of these predictions thinking about, okay, what are the characteristics of the light curve and the spectra that will tell us that actually these heavy elements are produced? So the heavy element production both powers the light curve, but also actually shapes the spectra. And then we needed to wait for a neutron star merger. And in August 17, 2017, which is my most favorite day after the birth of my kids, two neutron star, the gravitational waves from two neutron star mergers arrived to Earth after a long journey. What you see here is the frequency of the gravitational wave emission. So as these two objects come closer and closer, they start emitting gravitational waves at higher frequency. The amplitude increases. So you can see these very, very fast increase in frequency, and somewhere around outside the detector, they actually merge. The detector was basically not sensitive enough to see the high frequency exactly at the moment of the kiss. Yeah, they were almost, touching their noses, but then the detector was not sensitive to see the merger, but we knew that a merger had happened. So then we said, okay, if we can pinpoint the location, we have predictions of what electromagnetic signatures should accompany the detection of gravitational waves. So these are the positions in the sky from gravitational wave events. You're going to see something interesting that astronomers are not very interested when it comes to their way of dating, but this is, of course, dates. So this is gravitational wave 170817 that I talked to you about. You notice something interesting, that something happened, after June or so of 2017 that allows to position the gravitational wave with much more certainty. Yeah, you can see that the errors in the sky were actually significantly reduced. Why? Well, gravitational wave detection functions very, very similar to your ears. Yeah? And before 2017, we only had two detectors. So I want you to think about listening to sound. You have two ears. If you close your eyes, you actually cannot tell whether a sound is coming in front of you or behind you. And in that symmetry plane, in some ways, you're actually unable to tell direction. That's exactly what was happening. We had two detectors in the US, and we had these sort of bananas in the sky that we didn't really know where the gravitational wave came from. Our ears, gravitational wave detectors have polarization information, so they worked a little bit better than our ears. That's why you see the sharp edges. But still, trying to search for an electromagnetic transient in this part of the sky is impossible. But what happened? 3 days before the gravitational wave signals arrive to Earth, a third detector got turned on. So we had 3 ears, and we were able to much accurately position in the sky where the gravitational wave was coming from. And that was kind of an amazing luck. So I was part of the discovery team. It's the 1 meter to hemisphere team. Again, we're not very inventive in our names. We had 2 meter telescopes. We have a 1 meter telescope in Lick Observatory, which you saw, that I put a neutron star on top of it. And then we had a 1 meter telescope in Chile, the SWOBE telescope. And because gravitational waves and the universe doesn't discriminate between north and south, we were equally probable to see it either in the north or the south. So we had to basically cover both hemispheres. So this is the team that discovered the gravitational wave event first. I won't have a lot of time to tell you the story, but I'm just going to tell you that we had only a 1 meter telescope, and we were competing with telescopes that had 4 meter telescopes. And the key, and a lot of that, we owe it to David Coulter here with his teacher, I Want to Believe, that he said, well, rather than actually tiling the entire sky looking for an electromagnetic signature, we know the galaxies in that volume. So actually, let's just look at the individual galaxies. Let's list the galaxies as which ones we think are the most likely to host this event, which generally are the more massive galaxies. And because of that, we discovered the gravitational wave signal, the electromagnetic counterpart of a gravitational wave signal, about a minute before other teams. So this is the discovery image. The signal was incredibly blue early on, and then it turned red. And one of the big predictions is that if these heavy elements were present, the light was going to be incredibly reddened. And in fact, the spectrum had all the characteristics that we now with certainty know that heavy elements actually form in this event. So just to give you a feeling, well, how much gold do you think one of these events produces? Well, it produces of the order of about a Jupiter mass of pure gold. Jupiter has 10 to the 30 grams, 10 pounds per gram of gold, 10 to the 31 pounds. That's a lot of, it's a very rich event. If this is not impressive enough to you, this is the equivalent of the gold content in about 1 million stars. What does that mean? That these very rare phenomena produces so much mass of these heavy elements that it can actually disperse them and synthesize all of the heavy elements that we need in our universe. And this was deemed the science discovery breakthrough of the year, and something that I'm incredibly proud is that in our team, all of the papers were led by grad students and postdocs. So the question is, well, how many neutron-star mergers are in your body? And the answer is it took about tens of thousands of neutron-star mergers to make the gold in your body. Why? Because these have happened throughout the history of the Milky Way, and this material has been constantly mixed into the interstellar medium, and then new stars have actually been formed until ultimately the sun came from a cloud whose combination of gold atoms, included tens of thousands of neutron star mergers. Now, if you think about your oxygen actually requires hundreds of millions of supernovae. Yeah? So those oxygen filaments that you saw emanating from one supernova, you require hundreds of millions of those ultimately to mix within the Milky Way. Now, because this concept is kind of mesmerizing and a little bit hard to comprehend, we actually did the following simulation. So I'm going to turn off the lights. This is my favorite simulation. So this is going to show the formation of a Milky Way-like galaxy, similar to ours. And the simulation is going to stop when a cloud forms that has very similar properties to the cloud that we think gave rise to our solar system. It has the right metal content, it's at the right distance from the center of the Milky Way, and it has the right mass, okay? And then the movie is gonna stop there, and actually it's gonna play back, and it's gonna trace where those atoms that gave rise to that cloud came from, yeah? So what you're gonna see is sort of the genealogy tree of oxygen in your body, cosmologically speaking. I'll point out if you don't see the cloud, but I think it's pretty evident in this. Yeah, so this is a Milky Way spiral-like galaxy. You saw the cloud, then the movie stops and starts playing backwards. And starts basically following the trajectories of your oxygen atoms. So as I said, mixing in our own Milky Way has been so effective that your oxygen atoms have been everywhere. But then you start seeing, oh my God, what's happening? Some of the oxygen atoms are actually leaving the Milky Way. Why is that? Because about 30% of your oxygen atoms came from other galaxies that fell into the Milky Way. So you're not, your atoms are not only extrasolar, but they're also extragalactic. Yeah? And you can see here all of the trajectories. So these are smaller satellites that ultimately fell into the Milky Way, also bringing the oxygen atoms that ultimately landed in your body. Yeah? So when you think about being active travelers, your oxygen atoms have been incredibly active travelers. They have crossed the Milky Way many times. Not only that, they're actually being brought up by, smaller galaxies that fell into the Milky Way. So just to end, I wanted to just give you a feeling about why these atoms are incredibly important. So particularly thorium and uranium, their half-lives are so long, are giga-years long, that the vast majority, in fact, almost all the energy injection in the Earth comes from these two elements. And they're powering these fluid currents around the inner core that, when coupling with rotation, give rise to magnetic fields. So if we didn't have these two elements, basically the Earth will have no tectonic plates, no volcanic activity, and ultimately no magnetic field. The sun is being rather irreverent lately, throwing these incredibly powerful, flares. It's in a high state of magnetic activity around sun, and we have this magnetic field that protects us. This is a photo that I took in Northern California, where you can actually see the aurora boreal, which is like incredibly unusual at these latitudes, simply because the sun was just so incredibly active that it was sending these high energy particles. So if we didn't have these two elements, we wouldn't have a shield, and we wouldn't exist, because the ionizing radiation, particle radiation, would be so strong that life could not exist in the surface of the Earth. So if you don't care about platinum and gold, you should care about uranium and thorium, and therefore you should care about neutron star mergers. Okay, I want to end with a note about, I told you, well, uranium and thorium are fairly heavy. When the Earth was actually first synthesized, it was molten. That means that a lot of the heavy elements actually fell into the core. And for a long period of time, people say, well, what about all the gold? You talked about all the gold that we have in the surface. Where does that come from if the vast majority of the gold on Earth actually sank into the center? Yeah. And the answer is from asteroids. Yeah. And from basically impact in the surface of the Earth brought these heavy elements. If you have heard that we want to go and mine asteroids, it's because an asteroid has a gold content similar to your body, about 100 times higher than that of Earth. And therefore, so basically what ended up happening is we were bombarded, and then gold was concentrating in these high pressure environments, and then you produce these basically gold nuggets. So ultimately, the fact that we have these heavy elements in the surface is all related to the bombardment history on Earth, which is ultimately intimately linked to the presence of Jupiter. Anyway, so I wanted to finish with just one story, which I think ties together this idea of where we come from and our recycling. So I'm originally from Mexico. My grandfather was indigenous from Ojo Caliente, Zacatecas, and he was part of the descendants of the Olmecas. I don't know if you've seen these big heads, Mexican heads on stone. And he told me this story, and he said, when you're first born, your essence is synthesized, and your essence comes rushing to Earth to meet you. So very similar to sort of if you think about the asteroid impacts. But in its journey to you, it breaks into a million pieces. And it says when you gain consciousness, you're actually going to feel incomplete. You're going to feel like you're missing something. And it says, but rather than these being an opportunity for you to be sad, it's an opportunity to be happy. Why? Because those pieces, it's not like they fell into the floor and you have to pick them up. They fell into other people. And only by sharing them with them, you become more complete. Yeah? So in your journey to become a more complete human, every single individual that you meet has a part of you and an essence. So I think if you think about the recycling of oxygens, it's the same. No? Now, because we're all in this room, we're taking our own human history together and sharing it. So I will end there, and I'll thank you for your time, and hopefully the next time you see a gold ring, you'll think about the extreme conditions that took to actually make gold. Thank you.
Wonderful stuff. Thank you so much, Enrico.
No, thank you.
Do we have any questions for our speaker? You were too profound. You wowed them too much. Yes.
Is it right that some heavy elements are created by supernovae themselves?
It's a big debate. If I give you the more academic version, is there's two processes that make heavy elements that are heavier than iron, and it has to do with neutron capture. So when you capture a neutron, you become radioactive. So if the capture of neutrons is slow, we call that the S process. And if the capture of neutrons is fast, we call that the R process, rapid process. So most of what I told you comes from the rapid process. Now the S process happens inside stars that are more massive than the sun, but they happen slowly, some of these heavy elements. Something like gold and platinum are particularly just R process, the same with uranium and thorium. Now there's significant, if you open a textbook, you will say like supernova are responsible for the vast majority of heavy elements, but that textbook is not right. When you look at the distribution of the abundance pattern of the sun, you see 3 peaks, and the kind of light, medium, and heavy peaks. And we think that maybe the light peak was produced by normal supernovae, but the second and third peak require much more extreme conditions that supernova cannot meet. So we need either neutron star mergers or a very exotic type of supernova explosion that may involve like a magnetar or something like that. But in reality, yes, the kind of standard story is being challenged.
And when you say, sorry, Chris,
Yeah.
Light, medium, and heavy, I think you said, they're just element groups beyond iron, are they? So the greater the atomic number, the more difficult they are to make.
Yeah, the way that you should think about abundance peaks in the universe is that they basically are correlated with nuclear stability. So if something is stable, you can think about, and particularly if they have these closed neutron shells, they don't want to capture more neutrons. So then you send a huge amount of neutrons and they kind of stagnate at that particular peak, and then a peak is basically generated. So there's basically 3 neutron closed shells that give you the first, second, and third peak of progressive heaviness. No? And if you actually look at a periodic table, iron is the iron peak elements are the last elements that have equal number of neutrons and protons, and then all the other heavier than that require a progressively larger fraction of neutrons to be stable. So something like lead is incredibly heavy, but it has almost twice as many neutrons as it has protons.
Yes, please.
I don't know if this is a silly question, but
There's no such thing as silly questions.
is there like a number for like the right condition or like the cloud that you're talking about for it to create like a sustainable condition for life to flourish? Is there?
Yeah, I think so. This has to do with the process of star formation. No? So when we think about a cloud, we think about a molecular cloud has to be born, and that molecular cloud will collapse and probably form a huge number of stars, and we expect that one of them will be the sun. That's usually how the process of star formation is. And when we were looking at this simulation, we wanted really to have it at the right distance from the center of the Milky Way and with the right abundance, particularly, making sure that all the elements until the time where the Earth or the sun or the cloud was formed had very similar to composition to the one that we have today. And so when we looked at the sun, we actually we know its composition very well, and we just want to imitate that composition more broadly speaking. But generally, the process of star formation is you have a molecular cloud that it's maybe, hundreds of thousands more massive than the sun, collapses and gives rise to a lot of stars that are similar to the sun. So our solar neighborhood has stars that look very, very similar that we think may be formed from the same episode of star formation.
Any more? Yes.
So again, it might be a silly question, but you can, a with the parallels. You can dig ice cores, for example, to go back in time and learn about history through looking at ice. Do you think there's ever a point where we can learn about all these other really faraway places through what's...
Amazing question. That's like an amazing question. Yes, not only in ice, but actually in the deep ocean. So what people actually do is they drilled, and of course, because sedimentation, you go back in time and you're looking at layers that are progressively older. What people actually found is radioactive material. So we have found, for example, radioactive nickel that we think came from the nearest supernova explosion to us that happened about 10 million years ago. So the supernova exploded, produced all these basically freshly synthesized elements. For some interesting reason, they got into a dust form. The dust is able to basically go through the magnetic pole, sediment into the ocean, and then basically gone. And we also seen uranium synthesized where so as the solar system is basically going around, it's actually capturing kind of a broad range of radioactive material. So by actually people doing, the ice doesn't give you a lot of back in time, I think maybe 1 million years, but the ocean can give you hundreds of millions of years. So people are doing those experiments to try to capture kind of freshly synthesized material as we surf around the Milky Way.
Wonderful. Maybe time for one more if anyone's keen.
Or
If
not keen.
You explained everything perfectly.
Thank you so much for giving me your time.
There'll be a refreshment break, and then there'll be a talk back in here. There'll be a planetarium show, courtesy of the Cambridge Astronomical Association, in about sort of 15 to 20 minutes or so. Fantastic.
Thank you.
Brilliant stuff. Thank you so much. Yeah, that movie.
It was half an hour, more or less.
More or less, but yeah.
I'll try to
Everyone was very happy. It's like, so yeah, no, it was wonderful. Thank you.